So this is going to be about tools and tool design, and it's very straightforward in terms of going the overview of hand tools in the context of ergonomic applications and so on, and the important characteristics of grip and endurance. We're going to be mostly focusing on hand tools and design of various things that use for our hands, and we're going to look at the ergonomic characteristics of such tools and the basic mechanisms of why some tools perform better than others. We're going to get into a little bit of the math. Just as a heads up on this, there will be some mathematical equations expressed here. All I want you to really do from this is understand the concepts behind them in terms of design. Some of them are pretty straightforward. Some of them, though, may be a little counterintuitive until you really think about their design and why they work and why others don't. Tool safety, we'll touch on that. We're starting to move into that realm, and then distinguish a good tool from a poor tool. So to start out with, we all have, we can go all the way back to antiquity and look at the various tools that have been developed over time. And there was an article that came out. It was, I believe, it was in Georgia, not the state of Georgia, but obviously the country of Georgia, where they found a fossilized skull, complete fossilized skull. The person's about maybe that high, and has kind of a long face, but is definitely humanoid, and goes back to about 1.6 million years. And in this particular area, they found baby skulls and things of that nature, and saber-toothed tigers and all the things that ran around at that time. But what's interesting is that many around that particular site, that dig, they found a bunch of stone age tools used by man back then, where they thought, well, when did they start inventing tools? And most of it, obviously, is the hunting side of things. And as you recall, the whole reason we're walking right on our hind legs, not walking on all fours, is why? Remember from the first lecture? Why do we do this? Carry stuff, right? We can carry stuff a long way doing this. Right? So that's the reason we walk on our hind legs, because we're doing all four. You can't really carry a whole lot on your back, pretty worthless, and so you can explore a lot further when you can use your arms to carry things. And in order to carry things, you need to develop tools in order to hunt. And these are some of the earliest tools that are found, called the Clovis points and flints. And this is in the Americas about 9,000 BC, and you can tell from the serrated edges and so on. They'd fasten these to spear points. And then throw them. And the limitation, though, is that when you fasten the spears and throw them, there's only so much energy you can throw. And if you're trying to hunt down a mastodon or something of that nature, you're going to have a tough time penetrating the hide from a throw. So often what you have to do is go up and literally charge this thing, right, and then stab it. And then several would have to do that, several hits, in order to bring this thing down. And that could be very dangerous. Right? So you had to come up with something a little more clever, and these are the spear points used, track them down. But what has been shown from around the world is this thing called a woomaroo in Australia, but in Europe and the Americas, it's known as an atlatl. I'll talk a little bit about that, but basically it's a stick that helps you lever the speed of an arrow, and a spear in this case, by being able to whipsaw and throw it, and it goes about 10 times the speed and about 6 times the force as something thrown from your arm alone. So it's really a very good tool. The thing that's unique about this Australian woomaroo is that it's highly coveted because it's more than just a throwing tool. At the end of this right here, there's a little a barb, and what happens is that the spear has a dimple in the end of it. And so when you put the two together and you throw it and you flick it, it goes a lot further, faster, and more powerful than if you do it by hand alone. But and he shows here he's getting ready to throw this thing, and it can be quite accurate as well with some practice. And this is your atlatl right here, hunting, and you can see the same kind of concept right there. And being able, and there's you can see it. and the technique for throwing is. And there are actually groups out there. I'm surprised Purdue doesn't have a Addle club or something. It should be kind of interesting. So the things they would hunt in the outback would be kangaroo, wallaby, and so on. And these things are pretty fast. By the way, don't ever get in a fight with these things. You think they're all cute and everything like that, and they're going to box you with their little arms. What they do is actually their feet have claws and their tail, and so what they'll do is they'll flip around, they'll whip you, they'll break your legs, and then when you're down, and then they'll jump on you and they'll claw you and start ripping out your guts. So don't think these things are all that friendly. Just in case you're wondering, it's a cute little thing. It's not. This shows the woomaroo in the outback being used as basically a fire starter. Excuse me. It shows a little close-up here. And what they do is they get pellets, droppings from the kangaroo. And because it's organic matter, and then they get a little bit of clippings and so on, and they put the droppings in this brew, and they use their woomaroo, run it back and forth, create friction, and it starts a fire. So that's how they get their fires going in the outback. And if you can see the way this is shaped right here, it's carved out. It's a fairly hard piece of wood, and you can see it's channeled out right here. And what that's for is that after they start the fire, first of all, they've thrown the spear, they've killed the kangaroo, they bring it in, and I'll see if I got some other pictures here to show you. Start the fire, cut up the animal, and cook it, and then they use the woomaroo as a plate, basically, to hold the food and to eat from it. And go back. You can really see on this end right here is a sharpened point right there, and that's used for the cutting part of the animal. So basically, it's like a Swiss Army knife, in the outback, in which that's all you really need is that. If you have a good woomaroo, then you pretty much have anything that you need. You got something to hunt with, you got something to eat out of, you got something to cut up the animal with, you got something to start fire. These guys are set. They're pretty sharp folks existing in the outback, and ever since the Europeans have come to Australia, the Aboriginal people have not been a good fit in terms of the European society and culture and so on, because this is mostly what they did, is existing in the outback, and just free roamers doing their thing. They also showed many of the things you see people come back from Australia with boomerangs, right? And it's basically this little triangular shaped boomerang. And when you're in the outback, though, in the desert and so on, you don't need the boomerang, because the boomerang is designed, the one you're familiar with, is usually you find it around the coastal areas, and you throw it out to sea, and you hit a flock of birds. And the idea is to lead the birds and try to get one on the front end. If you're lucky enough, you can spin around, come back, and hit another bird coming back, and then you go out in the water and get it. If you miss them altogether, the boomerang comes back to you. Right? You don't have to go out into the water and get the dumb thing. Here, you don't need such a thing. You just need something that's heavy on one end, like an axe, and you pitch it. This is carved out of wood. It's nice and heavy, and you throw it, and it tumbles, and you hit the animal that way, and knock it out or hurt it, and then you run up and take it out. So that's an actual boomerang, not one that returns to you, but one that they can throw and hit the animals with in the outback. This is the red rock, called Ayers Rock, and Uluru is what the natives call it right there. 6 miles in circumference, by the way. It's a sacred site, and it goes up to about, I don't know, maybe 800,000 feet or so. And the Aboriginal people, it's theirs, it was given back to them, don't want you climbing around on it, especially if it gets windy, because once you fall off this thing, it's not a good ride down. It really it's pretty humbling. But on the day I was there, the wind wasn't up, and I got permission, and I went to the top, and there I was trying to look contemplative, and actually turned out looking stupid. But looking off in the distance, and the reason I want to show you that is the hoodoos are out here, and what happens is you can go around, hike around in these areas, and they heat up, and it becomes like an oven. So if you go there in the midday, a lot of people don't wander out because they get heat exhaustion and so on, and never get out of there. But it's quite a view from up there because there's nothing else for as far as the eye can see except for the hoodoos and Uluru right there. It's all flat for at least 1,500 miles. It's in such an amazing outcropping of rocks just right there. And that's why it's a sacred site, because it's so unusual. And then, of course, the night skies there look just like that, just pretty amazing. So if you ever get a chance to go to Australia, definitely do that. Hit Sydney and then go up to Alice Springs and to Ayers Rock. So getting to tools now. In terms of modern day, a lot of times we use these kinds of tools. We put an extended shaft on it to give us leverage. And when we get into hand tools, obviously we see them as extensions of the human hand. They enhance our capability and productivity for the users. Poorly designed tools or the use of the wrong tool can result in injuries. And I think many of you have probably tried to use a tool that wasn't designed for what it was supposed to do, and it didn't work very well. Ancestors developed a number of tools, and these are just kind of examples. For example, the foot claw here, a beaver right here, looking at a chisel, a duck, basically needle nose pliers and so on, a little hook right here from an animal's foot, and then of course a web foot from a duck, and a flipper for water and so on. So in many instances, earlier tools were used based on animals that were found that saw the job or the observation of that, and then man picked up on these things and developed the various tools that you see below to perform the same kinds of tasks. Now there is a thing that I'm going to test you on. Grip strength is the maximum momentary squeeze force, and endurance is the length of time a person can exert a specified force. So the difference between grip and endurance you should know, because the endurance obviously involves the element of fatigue, whereas grip is that we're looking at the overall force. And remember that experiment that we did in class, right? With maximum grip here, you felt that with the finger, and then if you got into an awkward posture, if you compromised yourself by as much as 65%, right? So this kind of thing becomes important. So when we look at grip strength, we really want to look at the maximum grip strength in the neutral posture. Both are important. And then we look at various aspects of the hand. We have size of grip, type of grasp or grip. And remember, the two things I'm only responsible for are the power grip, right, and precision. Right? Precision, just what you're using right here to write down, take your notes. Power grip would be like handling like a baseball bat or something of that nature. Age becomes a factor. Basically, you're at your prime in terms of maximum grip strength. Gender, the grip strength for men is greater than that for women, and this it goes across the spectrum, right? For so many things that we talked about in terms of cross-sectional area of muscle. Yesterday I was reading the Wall Street, and the Marine Corps is now doing a thing about allowing more women, or at least training them to get into combat roles, right? And one of the things that bothers me a lot about this is that they said so far they handpicked 16 women to go into these combat roles, and they have to do everything that the men do, pull-ups and push-ups and all this stuff. And knowing what you know, is this a recipe for failure? Yes or no? How many believe it's a recipe for failure for women? I should see all your hands go up, because it is. You're expecting the women to do exactly what the men are doing, and based on what you know they can't. They can't do it. They just do not have the muscle strength and muscle development to be able to perform. However, and I'm going to write the comment on the Marine Corps about this, I said, however, if you put women in specialized roles, for example, they might be pretty good. Now, getting away from any of your politics and personal views and so on, I believe that women, if they get put in specialized roles, let's say snipers, for example, they're probably pretty good at it. Take you out in a heartbeat, right? Or setting up booby traps. I think they would be really good at setting up booby traps. I don't know. But the idea is to specialize rather than saying we're going to have the women do everything the men do because we're not going to treat them special. I said, well, there's a difference in gender. And you said of the 16 that started out, they said not one passed all the tests. I said, well, duh, right? Because you designed it for these young guys to go out there and do it, and the tests, the way they're designed, are designed in such a way that the women will fail. And it just frustrates me that in these modern day and times that we don't even think about that kind of stuff. Just aggravating. So anyway, when we get into gender, these issues do come up. So you design it so that they can succeed and that they can be a part of something should they choose to be a part of something like that where they would specialize. But there's always a gender issue that comes into play for grip strength. Handedness, dominant hand, right? If you talk to a lot of the PTs and OTs around there, their big mantra is we want to make both hands as strong, right? Try to balance your strength and so on. I agree with that. But the fact of the matter is most of us are going to be stronger in one hand than the other. Vibration comes into play in terms of grip strength. Vibrating tools force you to grab onto that tool harder than you should and could lead to some static loading. Gloves are important. That helps increase grip strength requirements, but sometimes you can overgrip. Why? Because it's hitting the proprioceptors on the fingers, and as a result of that, you tend to overgrip with gloves. So they keep them more. So while it helps maybe with slip resistance, sometimes you can have fatigue set in if you don't have the right gloves. In fact, one of my big things there, has anyone ever worked at, what do you call the foot-long place? Subways. Yeah. You work at Subways? Work at Subways?
Yeah.
What is the deal with those stupid gloves? I mean, if they invested a little more money into a good glove, right, something that fits instead of these big old plastic bags, productivity would go up, revenue would increase, throughput would be better. You know, that's a great project. But no, you know,
they just have big ones for girls' pants, or small ones.
Yeah, it's like, you know, duh. It's amazing. They just, you know why? Because whoever's in charge of that is focused on unit cost, right, rather than all the other information that would be very important in terms of, I like Subways, right? The problem is that I get queued up and I see a bunch of people there. I just could take forever because they're wearing those stupid little gloves. Sure. Anyways, gloves are important. Great project, by the way. And then, of course, surgery is important. It'll reduce, and we talked a little bit about the median nerve, cutting the transverse ligament and so on. That'll weaken the wrist. And a lot of times what happens is that when the transverse ligament heals back up again, a lot of times there's scar tissue there that may cause some problems down the road. So, the evolution of hand tools. In this case, we're looking at our ancestors through the Industrial Revolution all the way up to today. And what we have, and I've just finished off a book that looked at surgical tools being used in anesthesia and so on, and it's amazing just in a little over 150 years where we go in without any anesthetics at all and cut a person's leg off that basically had been shot or got infected and so on. Today's surgical tools that are being used that basically can go in and put a prosthesis on and be put under anesthetics and not feel a thing and come out in many ways. These prostheses can be better, as good as what was there before if they had some kind of impediment. So we've come a long way in a very short amount of time in terms of the tools that were used then versus today. So here's a quick pop quiz for you. Why is this an ergonomic hand tool? And it's a trick question. Is it an ergonomic tool? Yes or no? Those that haven't read ahead. How many believe it's an ergonomic tool? How many believe that it has ergonomic features, but it is a tool? There you go. Some of them read ahead. It has a feature in that you bend the tool rather than the wrist, right, in terms of going in. Now, if you're using those needle nose pliers to twist something, that's not a good thing, right, because it puts you in an awkward posture. But if you're using them just to pinch or clamp something in that position, that's fine. That works fine. So, the right tool for the right job. No such thing as an ergonomic hand tool per se. That's a question that you'll probably get asked again, so make sure that you got that down. The ergonomic benefit excuse me, of a tool depends upon its application. And the tool that is for one job, works great for one job, may not work for another. So realize that sometimes these specializations do come into play. So when we look at things to identify ergonomic aspects, we have forces, movements, thermal aspects, and vibration, magnitude, repetition, and duration all come into play. Mechanical advantages and features to reduce exertions and forces, and power tools that impart least force against the operator. In other words, you want to make sure that tool is doing the job for you rather than you doing the work for it. And I'll show you examples of that. So I like to ask the ladies this one. To get off my little soapbox here earlier, that ergonomic tools depend upon the task. Why are these pliers easier to use? So, ladies, why would they be easier to use? Based on what you know, what I've showed you, and I'll give you a little tip. It's the grip strength that I showed you earlier in terms of the digits and so on. So why would this be better for you than the other way around? Yes? What's the answer?
Probably the distance between the handles and it being upside down.
Okay, distance between the handles and this being upside down. You're close, but think not so much the distance, but are you stronger this way or this way? How many believe we're stronger with these two digits than these two digits? Ladies, are we stronger this way? And this one too, right? Remember our long bow demonstration a little bit earlier, right? Stronger this way. So the idea is that, okay, now you have it upside down. So if you have a stronger grip this way and you can grab onto the base of the pliers upside down, and guess what? Your grip strength is going to be stronger, right? Because the strength of your first and second and third digit is going to be certainly stronger than the fourth and fifth in the pliers. And so as a result of that, you can actually be able to turn or break something loose in this position than compared to this position, which is upside down. Why? Because now you have the spans that you're talking about, but you're now using the weaker digits to try to put pressure or grip force at the base of the pliers. Does that make sense? It's pretty intuitive, isn't it? I mean, once you think about it. So next time you're using a pair of pliers and you're struggling trying to break something free, try that. Just flip the pliers upside down and then try that and see if it works for you. I can say in most instances you'll find it'll work just great. So you have mechanical advantage here. So take-home message then is that this ergonomic has a task to squeeze the pliers to create strong compressive forces. The jaws is easier, requiring precise manipulations. Fine motor control would require you to flip the pliers around the other way. So as you're sort of tightening things up, getting ready to do that, you hold the pliers in the normal way. But when you're trying to break something free or do that final crank where you're really trying to tighten up, flip the pliers upside down, and you'll find you'll get a better grip on it. This one is a little less intuitive. It talks about ergonomic tools in terms of Phillips heads and flathead and hex nuts. This is our Torx right here, the hex. This is our Phillips, and this is our slotted right here. And what you might think is when you look at a Phillips is that, well, to me, Phillips might be more because, there's more contact area than a slotted head. So you're saying, well, which is going to require more effort? The Phillips, the slotted, or the Torx? The Torx, then, realize, is a combination of the slotted and the Phillips. It makes a marriage of the two principles. But actually what you find is that if you do the math on this in terms of contact points, this is the math right here. And again, I only hold you responsible for the concepts here. With slotted screws, actually, when you do the math on this, typically Phillips head screws require 6 times the feed force compared to slotted screws. You say, wow, that's weird. I never really thought about that. And that's maybe one of the reasons why these things strip out so easily. Right? You really have to put a lot of force on them so you don't strip them out. Here, what happens is that with the slotted, you can actually apply torque on the slot head. The idea being you're not stripping it, right? That you're going down. But you don't have to give it the same kind of feed force that you would a Phillips screw. Your take-home message here is that Phillips head screws require more force to keep the blade seated. Flathead screws need less speed force, but there's a greatest tendency to slip sideways, so you have to make sure that you lock it in. You don't put a lot of it. It's not out of the slip. The Torx heads have the advantage of the flips and the flat heads, and that's one of the reasons why a lot of people like to use them, because it increases the surface area, but you don't have to increase the feed force, which is great. And then this holds for manual and power tools in terms of being able to tighten or loosen these kinds of screws. So if we get into dealing with now diameter for handles, remember, what's a diameter for a female hand that's optimal on average? 1 inch, right? For males? 1.5, right? So we got to keep that in mind. But the idea here is that our long screwdrivers then easier to use than short screwdrivers. And this one here is, it makes sense if you start thinking about it in terms of torque and angle. So any sailors in the group here? People who've done sailing and stuff? Okay. You know about the keel and so on, right? The keel going down and the sail going up, and the weight that you have to have in the boat. The keel, right? The ballast, keep things from flipping over. So basically, the more you catch the wind, right, the more torque you have, the faster you're going to move, right? So think about that in the taller the sail, right? So if you think about it in that way, think about the torque produced then is proportional to the handle diameter. Okay, there's your force times the diameter divided by 2. And when you apply this torque, in other words, it's an eccentric motion, right? When you're turning, it's not always exactly straight. There's going to be a little bit of torque to it, very much like sailing, right? Cutting through something. That when you look at your feed force, you need to keep the blade seated and so on, that if you look at the length of that shaft, 6 centimeters versus 25 centimeters right here, you need 15% more feed force and torque compared to the longer shaft going down in terms of the turn. So this math right here works out in such a way that it helps keep the blade seated and the longer. So next time you unscrew something or screw something in, think about the longer shaft. And the idea is that you're going to have to keep it under control when you're doing it. But it's going to be a lot easier than a short little screwdriver. Makes a big difference. So next time you say, well, what kind of screwdriver you want? Say, well, give me one with a long shaft, because I know that's going to be, based on what I know, it's going to be easier for me to be able to seat that screw or to loosen it up. And it's kind of interesting when you look at how that's applied. So your take-home message there then, longer screwdrivers need less feed force than shorter ones when used with one hand. Screwdriver length has accessibility, and then feed force is also reduced by using 2 hands or using a nut driver or a nut runner, and this is a powered screw gun. One of the guys that I went to school with at the University of Michigan, who's now at the University of Wisconsin, is an expert in this area. His name is Rob Radwin, R-A-W-I-N, and he has done a tremendous amount of work in the idea of tool design and pluses and minuses, and credit to him for working out some of these issues. One of the areas is tool balance. If you're thinking about getting Dad a tool, your dad is sort of a handy person, or your mom the handy person. I don't want to make it gender specific. One of the things to look at is balance. And if you look at the handle at the back of this tool, the circular saw, powered circular saw, on your right-hand side, look at the center of gravity there, and you know this now, that if you put all that weight out there, it's not going to give you as much control as if you move that handle up closer to the base of the tool. So in this, the one that's on your left-hand side shows that the handle's been moved forward, and it's a lot closer. Look at that length right here, and there's your center of gravity right here. And so what that means is that you're not dealing with any torque issues. So if all you're doing is just sitting on with a table saw and you're just ripping wood, this kind of thing, then really neither saw is going to show you much advantage. But if you're doing any kind of work, doing let's say vertical work or any freeform kind of work, I know it's a little bit dangerous, but certainly this tool on the left is going to be a lot easier to use because you're not having to fight the torque involved in terms of that tool trying to rotate out of your hand. By the way, a simple method to determine center of gravity, which is kind of fun. Take any thing. Let's say if I wanted to find out where the center of gravity is here, what I would do is just hold this by one point. I draw a line here, and then I would hold it suspend it from another point, and then I would draw a line here. And where the two lines intersected on here would tell me right where that center of gravity is for that particular tool in terms of its rotation, which is kind of nice. Where is that helpful? Let's say you're trying to suspend a tool or something of that nature, and you want to find out where it would be in terms of balance. That's the way that you would do it. You would suspend it at that point where it wouldn't try to rotate out. Kind of a nice little technique there. So, tools that maximize exertions in, two hands are much better than one alone. And you can see this one's been rotated up right here. The right hand and the wrist motion and going across. Usually there's a handle that comes out on these right here that keeps you from getting your hands in the way and getting them cut. And then weight obviously is a factor, and here you can see in terms of hand distance and feed force, the further back the hand is right here from that center of gravity, the more torque that's going to be loaded on the hand in terms of the fatigue that sets in. So take-home message then is locate tool handles to maximize tendency to rotate to minimize rotation in the hands. In other words, get that handle as close to the weight of the tool as possible. Two-handed operations distribute the weight evenly. So two-handed operations are good. Make sure you don't put one in the way of sort of cutting yourself. Take-home message then on all of these is that it's possible to quantify, determine which tools minimize exertions. Important tool parameters include mechanical advantage, balance, the type of head that's used, a Phillips, flat, or a hex, tool geometry in terms of its compactness and use, posture and work location, tool speed, and reaction force. Reaction force is that kickback force that once something gets seated, if you notice that sometimes a tool will kick on you, that's the reaction force that I'm talking about in this example. And then the best tools are the ones that are matched to the task, and that's really the essence of what ergonomics is all about. So hand tool safety. General hazard controls for this is that the right tool for the right job, know the hazards. Remember Dr. Montgomery's example of different metal characteristics of a carpenter's hammer versus a ball peen hammer in reading his chapter. In this case right here, we have a preening hammer, but the one that really stands out in my mind is a ball peen. The peen part is when bolts would be basically put into putting two metal pieces together, and then it'd be superheated, and then the peen part, the rounded part, was actually used to round out that rivet on the other side, and then when the metal would cool, that bolt would cool, then it would basically actually pull the two metal pieces together. And you see this quite often on bridges, older bridges. When you cross them, you look up, you'll see that rounded part up there. Of course, they used much larger hammers in the day to get that kind of rounded edge, but at one time they were just straight out like this, but they were superheated so that you could pound them into position. And these tend to be much more hardened in terms of the metal, and that way you don't have any metal pieces breaking off if you're trying to hammer it into masonry or things of that nature, versus the one below. These claw hammers right here, these are much softer and tend to splinter a little bit and could go into your eye and hurt you. So hazards then are carpenter's hammer. These are made for driving and pulling nails. Workers should not use them for all-purpose hammers because they can be used as a crowbar, for example, driving chisels or other hardened driving screws. Then the carpenter's hammer is also not heavy enough to drive hardened masonry nails. Use a ball peen hammer. That's the one that I talked about with that characteristic design, like this. Your handle going down, so that's that rounded part. That's the part we're talking about right there. It's a more hardened steel, safer. And the hazards then with the ball peen, hardened. It's on one side. Obviously, you can't use it for pulling nails and so on because it's specialized. And the peen, obviously, for the soft metal rivets and so on that I talked about a little bit earlier. Using things correctly, socket wrenches have torque limits. So what they have, these things that you saw a little bit, either called a cheater bar, right, putting a little rod in there and pushing it out. These things can strip and break on you, and you can slip and fall, so you have to worry about that. Inspecting tools regularly to make sure that they're in good condition is important, and sharpening edges of tools and so on so they work efficiently is also important, because in many programs, as I mentioned to you, I'm doing some work with Bath Iron Work, and when I first went and did some inspections there, they had a tool crib, but they didn't have a maintenance department. They have a whole maintenance department now where they do nothing but sharpen tools and upgrade tools and things of that nature, because they know that the value of good craftsmanship and the work that's being done there is far greater than just using a simple tool and using that tool poorly or letting that tool go bad. So that comes out quite well in a company like that. But most places that you look at for things like that, remember that a maintenance program is important. Tool guards are important. Knife guards, I'll show you some examples of that, from slipping and your head getting sliced on a blade. Handle design. This is with the bent pliers you saw a little bit earlier, and when I asked you, I said, this is an ergonomic tool. No, most of you knew it had an ergonomic feature in terms of bending the tool rather than the hand. This goes all the way back to the 1950s, where work was done there, where they put an angle in the tool. Then there was this thing called the Bennett handle. And what's interesting, there's always a story behind the story. So this guy Bennett was not a scientist, wasn't an ergonaut, wasn't anything. He's just a guy who came up with bending the handle, because he thought that if you bend the handle, you don't have to bend the wrist. You're going to get more efficiency from that tool. And he was right. Conceptually, he was right. And he came out and he promoted the Bennett hammer, right? And he made a lot of money. But everyone came out and said, why'd you pick 19 degrees? Why didn't you go with 20 degrees or 21 degrees or 25 degrees or 15 degrees? And it finally came out after so many years. He said, well, I simply looked at my heart line on my hand right there, and I calculated that from going across the knuckles right there, and that angle difference right there was about 90 degrees, and that's what I came up with. No other reason. It's interesting. It turns out that that's fairly close to being able to neutralize a hand. The striking part is going to hit, before, right, if you've got a bent handle, than if you have a regular tool. But it could have been 20 degrees, it could have been 21. The principle still would have been the same, but he came up with 19 and said, that was the magic number. And all I had to do was just actually his lifeline that he was able to draw from. I thought that was quite interesting. That all came out. So, anyways, Bennett, just a guy who had an idea, and he got it out there, promoted it, did some good marketing with it. Conceptually, it made a lot of sense, and he made a lot of money. So this is your knife, and this is your guards right here. And the idea is that these guards are to keep, from when you're cutting or pulling, to have your hand come in and get sliced. By the way, if you're going to slice yourself, it's good to have a really sharp edge rather than one that's not so sharp, because it gives you a jagged cut. So I'm not advocating that you cut yourself and use a sharp edge, but sharp knives will give you a cleaner cut than a ragged one will. Here's your bent handle that I was talking about right here. This here you have the straight handle, and there you have your bent handle at 19 degrees. And because it's bent, then the striking head that you see right here is going to hit first, as opposed to the handle that's straight up. Right. So important concept. Power tools in. This is a sort of lockout button to start it up. Most of these that you see, some of them are very awkward, because you almost have to use two hands, right? One to press the lockout switch, and then the other to activate it, right? And some of them, if you push the button, it holds the trigger in place and runs for as long as you want. Some of them, they're just not going to, they'll be activated as long as you have it, but when you release it, the button flips back and locks you out until you press it again. Those are fine. A lot of that's because of safety issues. There are interlocks then, are found on lots of things. I mean, many of you have probably experienced, how many of you have cut grass with lawnmowers and so on? Many of you have experienced that, right? When I was growing up, we didn't have any of these pull bars that basically are kill switches, if you will, that if you stop and you released it, right, the thing would die, right? The lawnmower would die. And the idea of that is that if you slipped or fell and you released that hand bar, your foot doesn't go underneath, right, and chop up your toes. And there's a lot of that happens every year, by the way. Lots of amputation, toe amputation, because people slip and fall. Well, they incorporated these bars in to be able to keep the balloon moving and the kill switch there. They released it, but what a lot of people do is they just don't like getting down there and having to pull the dumb thing again. So what do? Usually you use a piece of Velcro or tape, right? And they just tape the bar down and I'm just going to have it taped down until I'm done using it, right? Which kills the whole purpose of that being done. So then the idea is that, believe it or not, if someone loses their toes in a process like their falls or loses their fingers or whatever, they slip, and they got this thing defeated by using Velcro. So believe it or not, you can take that to court and go after that manufacturer. In this case here, I know some issues in the past, like Briggs & Stratton, for example. This is the engine maker. The idea being that Briggs & Stratton should have anticipated that someone was going to do that. That was going to basically defeat that kill switch. And because they didn't think this through, that someone would actually try to just nullify the whole thing, that they're now responsible for it. It's amazing, how the laws work in this thing, despite the fact that this company did everything it could to be able to make it safer to operate its engines. But it's interesting how that whole process works. And they call it a dead man switch sometimes when the trigger's released. A lot of times you find these, I'm writing one where it's now on the seats, right? If you raise up or fall off the engine dies. So, I'm not going to hold you responsible for this because you've got a lot on your plate with the extra credit. But what I've done in the past is I've had students work on tools from the Stone Ages to the Middle Ages, the Modern Ages, and so on. It's always interesting to me the ideas that some of the students come up with. So you don't have this assignment this time on the ledge output because of the extra credit we did on the molecular hub thing. But it's something to think about, next time you get into this. Is look, if you're dealing with tools in your project, look at something that originally was created to modern day.